Namaste to all. Welcome to my channel MA Tuitions. Please like, share and subscribe my channel. The last class we have discussed about the chapter 1 real numbers. In that we have studied about Euclid division lemma and Euclid division algorithm. Today we are going to discuss exercise 1.1. Here is the first question. Find the HCF of 135 and 225. To find out the HCF, we have to use Euclid's division algorithm. Okay, Euclid's division algorithm. In this 135 and 225, 225 is greater than 135. 225 is greater than 135. So what we want to do? You just divide this 225 by 135. Okay, 225 divided by 135. You will get 135, remainder will be 90. So we can write this 225 as 135 into 1 plus 90. 135 into 1 plus 90. Here the remainder is 90, it's not 0. So we want to continue this process. Just take this 135, this divisor 135 and divide with 90. Okay, just 135 divided by 90. One time it will go 45. Then we can write 90 into 1 plus 45. Again here also remainder is not 0. So we want to do again. Then write this divisor here. 90 will be equal to, that we know, 45 into 2 is 90 and the remainder is 0. Which means this divisor is the HCF of 135 and 225. So we can write the HCF of 135 and 225 as 45. Got it? Next question. Find the HCF of 196 and 38,220. What we want to do? You just divide this 38,220 by 196. I have already done here. Please go through the steps and we are getting the quotient as 195 and the remainder as 0. So 38,220 can be written as 196 into 195 plus 0. So here the remainder is 0. So our answer is 196. Our HCF is 196. Got it. Next question. 867 and 255. Here 867 is greater than 255. So we can write 867 as 255 into 3 plus 102. 255 into 3 plus this remainder 102. Here the remainder is 102. It is not equal to 0. 255 as the multiple of this 102. Just divide 255 by 102. It will go 2 times 2 into 204. It will be 51. And here also remainder is not equal to 0. So we can write this 255 as 102 into 2 plus 51. Again 102 equal 102, that we know 51 into 2 is 102 and the remainder is 0. So we can just stop this here and we can write the HCF as 51. The divisor 51 is the HCF. So here the HCF is 51. So to find out the HCF of the larger numbers, we are using Euclid's division algorithm. Second question. Show that any positive odd integer is of the form 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5 where q is some integer. Okay, so what is the question? We have given some integer. It is q and it is an odd integer. Odd integer means it is not a multiple of 2. It will be of the form. It may be either like 6 cube plus 1 or 6 cube plus 3 or like 6 cube plus 5. That we want to prove. First we want to write Euclid's division lemma. What is that? It is A equal to BQ plus R where 0 less than or equal R less than B. That you all know, isn't it? So here we need the odd integers just like this, 6q plus 1, 6q plus 3 and 6q plus 5. So here b is 6. We are taking this b as 6. Okay. So we are going to write this a. Instead of b, we are substituting 6. So we will write 6q plus r. Then the remainder or the r will change. That means 0 less than or equal r less than b is 6. So we have to write here 6. Then we will get 0, 1, 2, 3, 4 and 5. These numbers are the possible numbers for r, possible values for this r. We will substitute all these values in this equation. Then we will get a equal to 6q plus 0, which is equal to 6q, which is not an odd number, which can be written as 2 into 3q. It is an even number. So this is not possible. Then we will take a equal to 6q plus r. Here r is 0, here r equal to 1. Okay. 6q plus 1. Here 6q is an even number, isn't it? This is an even number. Even number plus 1, which is equal to an odd number. So this is a possible condition. Then next, we will take r equal to 2. Then a will be 6q plus 2. This is an even number. 6q is even and 2 is also even. Again, we will get an even. So this is not possible. Then if we are taking 3, a will be equal to 6q plus 3. 6q is an even number, 3 is an odd number. So we will get even plus odd, we will get an odd number. So this is okay for this condition. And r equal to 4, a equal to 6q plus 4. Here also we will get even plus even, an even number. This is also not possible. And r equal to 5. Okay, the last condition, r equal to 5. A will be equal to 6q plus 5. 5 is an odd number. Even number plus odd number will give an odd number. So this is a possible condition. So only these three conditions are possible. That means if q is an positive odd integer, it will be of the form either 6q plus 1 or 6q plus 3 or 6q plus 5. Understood? Third question. In an army, there are 616 members and 32 members of an army band. Both want to attend a parade. These 616 members have to stood up behind these 32 members. Got it? So, in how many columns they can arrange? That is the question. So, we want to find out the HCF of 616 and 32. Okay, HCF of 616 and 32. So, we have already studied the Euclid's division algorithm. We will divide the 616 by 32. It will go one time, 32, 9, 2, 29, 296. It will go 9 times, I think, 288. The remainder will be 8. Okay, so we can write 616 as 32 into 19 plus 8. Again, this 32 should be written as a multiple of 8. Then 32 will be like this. It is 8 into 4, that we know. And the remainder is 0. So we are just stopping this and we found out this HCF as 8. So there will be 8 columns. Got it? Fourth question. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1. So here it is positive, just a positive integer, not any even or odd integer. So we just want to use this positive integer. The concept is positive integer. First we want to find out what is the number. The positive integer can be written as a equal to bq plus r, where 0 less than or equal r less than b. This we have studied in Euclid's division lemma. So we are writing this also here. And we want to find out the square of this number. We want to find out the square of this a. That is, we want to find out a square. And this a square will be of the form 3m or of the form 3m plus 1. This we want to show. Got it? So, first we are going to find out this a. Here, we need this 3m and 3m plus 1. That's why we are taking this b as 3. Got it? We are taking this b as 3. Then this a will become this 3q plus r, where 0 less than or equal r less than 3. So the reminders will be r will be 0, 1 and 2. So we can write this a as 3q plus 0, that will be 3q. Then if you are using this 1, then it will be 3q plus 1. If you are using this 2, a will be 3q plus 2. So we got the positive integers in the form 3q or 3q plus 1 or 3q plus 2. Next we want to find out the square of this number. We are just squaring. A square equal 3q whole square. It will become 9q square. This is of the form 9q square can be written as 3 into 3 q square. Am I right? 9 can be written as 3 into 3 and this q square. So this, instead of this 3q square, we are substituting m. 3q square m. Then it will be like this 3m. So the first condition is okay. Move on to the next condition. A equal to 3q plus 1, just square. A square equal 3q plus 1 whole square. So this is of the form a plus b whole square. Am I right? A plus b whole square equal a square plus 2ab plus b square. Okay. So just using that formula, we will get 3q square a square plus 2 into a into b plus b square. So it will be 9q square plus 3 into 2 6q plus 1. So we are taking the 3 from both the first two terms, 3 outside, then it will be 3q square plus, here 6 is 2 into 3. So if you are taking this 3 outside, it will be 2q plus 1. Okay. So I am substituting m for this 3q square plus 2q. Then only we will get 3m plus 1. Okay. So this square is also in the form of 3m plus 1. Then move on to the next one. We will get a square equal to 3q plus 2 whole square. Using this formula, a square plus 2 into a into b plus b square. So 9q square, 2 into 3 6, 6 into 2 12, q plus 4. We will write this 9q square plus 12q. 4 can be written as 3 plus 1. Am I right? 4 can be written as 3 plus 1. From all the 3 terms, I am taking 3 outside. Then it will be 9 is 3 into 3. So if you are taking 3 outside, it will be 3q square. And 12 is 3 into 4. So if you are taking this 3 outside, then it will be 4q. And 3 is 1 into 3. If you are taking this 3 outside, it will be 1. Then the 1 itself. And I am substituting for this m, then it will be 3m plus 1. So all these 3 conditions satisfies 3m or 3m plus 1. So hence the proof. The last question of that exercise, 5th question. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. This is just like the above question, but here it is the cube, and the last question we have discussed the square of that number. So first we want to find out the positive integer. By using Euclid's division lemma, any positive integer can be written in the form a equal bq plus r, where 0 less than or equal r less than b. Since we need here 9m plus 1, 9m and 9m plus 8, we are substituting b as 3. Okay, then a will be 3q plus r, and the r will change, the range of this b will change into r less than 3, 0, 1 and 2. R will be equal to 0, 1 and 2. Then we will write the number a equal to 3q plus 0, or it is 3q. And the next number a equal 3q plus 1 and a equal 3q plus 2. Now we want to find out the cube of this number. A cube equal 3q whole cube. 3 cube is 27 q cube. Second case, a equal to 3q plus 1. Just cube. A cube equal to 3q plus 1 whole cube. So here we are using this formula. A plus b whole cube equal a cube plus 3a square b plus 3ab square plus b cube. So this will be equal to a cube plus 3a square b plus 3ab square plus b cube. Okay. So this will be 27q cube plus 3 square 9, 9 into 3 again 27q. Here 3 into 3 9q plus 1. We are taking 9 outside from this first 3 terms. Then it will be 3q cube plus 3q plus q plus 1. Then we can substitute m for this 9m plus 1. So this is okay. 9m plus 1 is right. Here also we got this as. So we just stop here, you know. So it will be 9 into 3q cube. Okay. So it will be 9 into m. So we can write 9m. I just use m instead of this 3q cube. Okay. So these two conditions already satisfied. For this, here we want to find out the cube of this terms. A cube equal 3q plus 2 whole raised to 3. So a cube plus 3a square b plus 3ab square plus b cube. B means 2. So it will be 27q cube plus 9 into 3. 9 into 6, 54 q square plus 9 into 4, 36 q plus 8. So from all the 3 terms we can take 9 outside. So we are taking 9 outside. 3q cube, 6q square plus 4q plus 8. So instead of this I will write 9m plus 8. So every positive integer, the cube of every positive integer can be written in the form either 9m, 9m plus 1 or 9m plus 8. So hence the proof. So we have discussed all the questions in exercise 1.1. I hope all you understood all these questions. Go through the questions and study well. See you in the next class. Thank you so much for watching.